Welcome to another organic chemistry laboratory video. In this experiment, we'll look at nucleophilic substitution, the mechanisms of SN1 and SN2. We'll look at some techniques involving heating at reflux, workup with aqueous organic extraction, and we'll study how to determine ratios of materials in a mixture sample by NMR integration. Here's a reaction of a phenol, where the OH group is deprotonated by sodium hydroxide, and then it substitutes for a halogen on N-propyl bromide or isopropyl bromide. These will be in competition with one another, and our goal is to determine whether this reaction takes place by SN1 or SN2 mechanisms. We'll carry out the reaction and obtain a mixture of products, and the ratio of the two products will correlate to the relative rates of the reactions, and this should allow us to determine if the reaction takes place by SN1 or SN2. Here are some of the components we'll use in the reaction. The 2,6-dimethylphenol and the sodium hydroxide should be handled with gloves, and the 1-bromopropane and 2-bromopropane should be handled in a hood. Now we're ready to begin. First we'll portion about 0.2 grams of 2,6-dimethylphenol. Next, we'll prepare an apparatus for heating under reflux.
This is the rheostat. That'll go on here. It's a heating mantle. Okay. Plug in. Make sure it's right below this. All right. Same thing with this. Plug below here. This is our stir plate. Stir plate goes below heating mantle. Plug that in. Got a light on that shows that we're good to go. Okay.
Notice the lab jack underneath the stir plate allows the sand bath to be lowered when needed. This water-jacketed condenser will go on top of the reaction flask. There's two hoses, water in on the bottom and water out on the top. And this will cool the vapors of the boiling reaction mixture, maintaining a constant temperature and allowing the solvents to drip back down into the reaction mixture. In goes the 2,6-dimethylphenol into a round bottom flask, which will serve as the reaction vessel. Now we add half a milliliter of solvent, in this case ethanol, to the reaction mixture. And if there's any solid stuck on the ground glass joint, rinse that down with solvent. Next, we'll add sodium hydroxide, which should be handled with caution. It can damage skin, so make sure to wear gloves and eye protection. So here we'll add half a milliliter of sodium hydroxide as well, and then we'll be ready to start heating this reaction mixture. Okay, let's move it to the sand bath. We'll begin heating. We add the condenser. As the solvent boils, the condenser returns the solvent to the reaction mixture, maintaining a constant concentration of the reaction mixture and keeping it at the boiling point of the solvent. Turn on the water only to a trickle and make sure that you have your hoses clamped onto the condenser so that they don't pop off under pressure. As this begins to reflux or boil, you'll see vapors condensing in the condenser, dripping back down, and now it's time to add the alkyl halides. We'll add the 1-bromopropane, 0.5 milliliters, and the 2-bromopropane, again 0.5 milliliters, and the reaction will begin. Under ideal circumstances in the lab, we would mix both of these two together in a vial and add them at the exact same time. And so you should do this in the lab. 0.5 milliliters of each into a vial, return to your hood, and add them both at the same time. Now the reaction begins, and we wait. After about 40 minutes, it's time to work up the reaction. The reaction's complete and we're going to isolate the products. So we're going to use about 15 milliliters of methyl tert-butyl ether in portions to rinse the reaction flask into a separatory funnel. First 5 milliliters, then repeat. Another 5 milliliters. This will get almost all of the residual material out of the flask. You can repeat it even a third time to ensure a quantitative transfer. Okay, now we have all of our material in the separatory funnel. Our next step is to remove any remaining phenol, 2,6-dimethylphenol, from the reaction mixture. We don't want that in the product. So we're going to wash that out using aqueous base. This will deprotonate the phenol, allow it to go into the aqueous phase, and we can separate it from our desired ether products. So 5 milliliters of 1 molar sodium hydroxide solution. We'll shake with the separatory funnel, make sure it's closed, and vent it into the hood away from people. Now when the layers separate, the phenol will go with the aqueous phase and our product will be more pure. This is called an aqueous workup. Separating unwanted materials like starting materials or other aqueous soluble materials from the organic product. Okay, we'll repeat this with another 5 milliliters of sodium hydroxide solution. A couple more times. And lastly, we'll wash with water, 5 milliliters of water, to remove any remaining base from the mixture. And we'll have an organic solution of our desired products formed by the nucleophilic substitution. We'll drain this into another Erlenmeyer flask, and now we have to remove any traces of water. So here we use a drying agent, anhydrous sodium sulfate.
This. So drying agent. We're going to add our drying agent to swirling it. Good, it's clumping up. Perfect example. Okay, so we need more.
The drying agent will form clumps when it absorbs water. And when you've added enough, there will be some free-flowing solid left in there.
Now we're getting loose grains. Just a little more. And powder. There's powder moving everywhere. That's good. Alright, and that should be good for today.
Next, we'll move to the rotary evaporator, or rotovap. This is an apparatus to carry out distillation rapidly under reduced pressure to remove organic solvents from products. There's a more extensive description of this in our extraction video. The dried organic solution is placed in a round bottom flask attached to the rotary evaporator, and over a few minutes the solvent will disappear. What's left behind is just a small amount of oil. Might not be visible until you stop the turning of the flask, and that oil is the product mixture that we next need to analyze by NMR spectroscopy to determine the ratio of products. So we'll put 2 drops, maybe 3, into an NMR tube, and in the stockroom, staff will add deuterated solvent for the NMR analysis. Once the sample's prepared, it goes into an autosampler, and this autosampler can be used to automate the transition between samples. The samples are put into the NMR spectrometer, the autosampler you can see at the top, and the output from the instrument appears on screen, and the operator can manipulate the axes, change the range. Here's the typical output from this experiment. There's a multiplet on the left, a triplet on the right. The integration data are shown in red in both graphic format with the line rising over the peaks, and also in digital format below the x-axis. These data can be used to calculate the ratio of the two products that form in this reaction. Here's an equation that shows how to do this. You can pause this video to take a closer look at the equation. After you've completed that calculation, you should then be able to reflect on whether this reaction is likely to have proceeded by SN1 or SN2 based on your knowledge of the rates of these reactions and how they depend on substrate structure. Thanks for watching.